Okay, I think I've unmuted myself. Can everyone hear me in the back? Okay, awesome. We have audio. So thanks for coming out tonight. It's kind of fun. I'm usually up here, as Martine mentioned, introducing everyone. I did an AstroTours a couple years ago, but I wasn't actually involved as one of the co-directors. So it's kind of fun being back here, but especially after being one of the organizers for a few years now. But I'm going to be talking to you about a really awesome telescope, a really awesome mission that was called the Kepler Telescope, the Kepler mission. And it's something that has really motivated a lot of my research. And so I really wanted to share its story with everyone tonight because it's something that makes me really excited whenever I think about all the work that I get to do. But to think about Kepler and how it changed really everything we know about exoplanets, I just want to start out. We're thinking exoplanets, well, that's just an extrasolar planet. It's a planet outside of our solar system. And so if we're thinking about that, we should really just begin with thinking about our solar system to make sure that we're on the same page, to understand why everything Kepler found was so incredible, to understand what we knew before Kepler started finding planets beyond our solar system. If this will advance. Oh, there we go. It's being blocked. Okay. So in terms of the planets in our solar system, many of them have been known. They're the classical planets. The word planet actually comes from a Greek word for wanderer, as they were sort of wandering stars. And so if you're up tomorrow morning quite early, this does not have a direct line. We'll see. Oh, that was a bad idea. Oh, no. It's okay. Being a PhD student means that I'm an expert in troubleshooting. So we'll see. Da-da-da-da. Gonna go? No. What did I do? Try doing this again. No, there's no video. It got bumped. Nope. Thanks, we're good. Did it go up? Oh. Push random buttons. Okay. I'm not going to fiddle with that again. I'll just have to awkwardly point to make sure that I can advance. Okay, so if you're up early in the morning tomorrow at about 6 a.m., this is actually what you'll see just before sunrise, is that Jupiter, Saturn, and Venus are going to be visible. And so these are some of the planets in our solar system that people knew about for a very long time. And so there was one astronomer, Johannes Kepler, who made observations of the planets in our solar system, of the classical planets. And so Kepler's view of the solar system was this, where we had the sun at the center, and then Mercury being the closest planet to the sun, and then we had Venus, Earth, Mars, Jupiter, and Saturn. So these were the planets that Kepler knew about, and Kepler did observations, and so he tracked where the planets were in the sky and used that to figure out some laws of orbit, their motion around our sun. And so one of the really important ones that he figured out was that the orbit period around our sun is related to the size of the orbit. The size of the orbit. Planets in our solar system. Uranus was also then later discovered in 1781. So we had a seventh planet discovered by William Herschel. And then Neptune was discovered in 1846. And what's really great about the discovery of Neptune, one of the things that I really like about it, So it was a joint effort from a couple of people, Urbain-Le and Johann Galle. And so this was actually discovered using math, which I love as someone who does theoretical work. I do a lot of math. Math is fun. Math doesn't need to be scary. Math is just another way of describing the world. We all like to describe the world. That's what science is all about. But what people had noted was that the planets, in terms of where they were, you could predict their orbits very precisely. But Uranus wasn't exactly where people thought it would be. And so they were predicting that there must have been another planet that was tugging on Uranus, causing its orbit to change just a little bit from what we would have expected if there wasn't a planet there. And so if we think about why planets are even orbiting the sun in the first place, that's just from gravity. And the sun has so much more mass. Planets are all orbiting the sun. The sun pretty much just dominates everything in terms of the mass or the weight. But planets also have mass or weight too. They can tug on each other, and they have slight pulls on their orbits. And so you can actually predict the presence of another planet, even if you haven't seen it yet, based on what it does to another planet. So Leverrier, he predicted where it would have been, and then Johann Galle actually went out and observed it. It actually turned out that it was a complete fluke, that he actually, so the prediction for where Leverrier thought it was, there was something wrong with the calculations, and so it was just very lucky that Neptune actually was in the sky where they thought it would be. I'm sure astronomers would have discovered it eventually, even with the calculations being wrong, but I find it kind of funny that it was discovered through math, but the math was actually wrong. Okay, let's see if I can do this. So then, now we have the picture of our solar system, ready to move on and think about bigger questions. And so one of the questions we can ask thinking about exoplanets beyond our solar system is just how common is our solar system? And so to think about this, we can think about some of the properties of the planet. So one of the things we can think about is the radius of a planet, which is really just the size of that planet, how big it is. And so if we think of the inner planets in our solar system, we have Mercury, Venus, Earth, and Mars. They're all fairly small. Earth is the largest of the four. And then for the four outer planets, there's Jupiter, Saturn, Uranus, and Neptune, and they are much larger than any of the inner planets. And so there's a pretty big variety in terms of the size of planets in our solar system. Jupiter is about 30 times larger in radius or larger in diameter than Mercury. So another property of planets are their mass or their weight. And this is really just a measure of how much stuff there is in a planet. And it's typically going to be related to the radius of a planet, but it's not strictly related. But if you want to think about mass, one way you can think about that is sort of how it would be related to weight. Granted, you couldn't actually put planets on a balance or a scale, but this will do just to get a sense of how we can compare the masses of planets. So Earth is more massive than Venus. Earth is actually more massive if you combine Venus, Mars, and Mercury. Earth is a little bit more massive. So we could do something similar thinking about Jupiter. And Jupiter is actually more massive than the rest of the planets in the solar system. So in some ways we can actually think of our solar system in terms of its mass as basically being the sun plus Jupiter and then some debris, some extra stuff that sometimes it doesn't matter, but obviously they matter beyond just the mass because we are here on one of those little specks. And there's a much larger range of masses for the planets in our solar system. So Jupiter is about 5,800 times more massive than Mercury. So there's a huge range in mass of planets in our solar system. And then the other thing we can think about is the composition of planets. And so this is where we no longer just have boring little circles. We can actually look at what the planets are made up of. So if we look at the inner planets in our solar system, they're all rocky or terrestrial planets. They all have solid surfaces that are pretty much rocky and metallic in composition. They have some atmospheres. Venus has a gas atmosphere. Earth has a little bit of an atmosphere, thankfully we're breathing. In terms of Mercury and Mars, they have very, very thin atmospheres. If we compare those to the rocky, if we compare those to the outer planets in our solar system, these are very different in composition. These are mostly hydrogen and helium. They have some rocky material, some metals deep in their cores. But for the most part, the majority of their mass actually comes from hydrogen and helium. And so they're very, very different in composition. And what we're actually seeing here are really gas atmospheres. They have pretty large gas atmospheres around their centers. And so we call these gas giants. And so if we think about this, again, we have these three properties of the planets, and they are somewhat related to one another. You know, if you have a larger planet, it's probably going to be more massive. If you have a really large planet, it's probably then going to be a gas giant. So we can sort of sum this up. I have to be careful if I'm pushing my buttons too fast. But if you have a small planet, it's probably going to be a lower mass planet. If you have a small, low mass planet, it's probably going to be rocky. If you have a really big planet, it's probably going to be high mass. It's probably going to be a gas-rich planet. That's not always the case. We can also think about the properties of their orbits. And so we can think about their size. Well, thanks to Kepler, the person, we know that that's just related to the period of the orbit. And then we can also think about the temperature. You might be thinking, why is this related to the orbit itself? And this is just because the temperature of a planet really just comes from the light that it's getting from the star. For the most part, it's really just receiving sunlight. So in the case in our solar system, the planets are receiving sunlight, and that is really what's providing a lot of their temperature. So if you're close to your star, close to the sun, it's going to be hot. You'll have a sort of a warm zone in between, and then you're cold the farther out you get, because you're receiving less sunlight the farther away a planet is. But we can just look at to see if this is strictly the case in our solar system and compare Mercury and Venus. So if we look at their mean surface temperatures, or average surface temperatures, so Mercury is closer to the sun than Venus, but Mercury's average surface temperature is colder. Okay, it's not freezing cold. The mean surface temperature is still, that's fairly cold for a planet that's really close. So we can still look at its maximum surface temperature, and it's quite hot. But Venus still has the hottest surface in our solar system, despite being farther away than Mercury. And this is really just because Venus has a pretty extended, for a smaller rocky planet, it has a pretty thick atmosphere. And this actually traps in a lot of heat, has a lot of carbon dioxide, had a runaway greenhouse effect. If this ever happens on Earth, we are doomed. It will not be good. We should take care of our planet. Venus is a good test case in what can happen when your surface starts to get hotter and hotter and hotter. And it is hot enough, I believe, to melt lead or something on the surface. Basically, like any spacecraft that have landed there were a few in the 70s, stopped functioning pretty much right away. They had like a chance to take a photograph, and then they failed. So we want to think about temperature. It's sort of related to the period, but it also somewhat depends on the composition. So for now, we'll just stick with the period as a property of an orbit that we can care about. So we want to go back to how common is the solar system. We can just think about those different properties related to then to exoplanets. Now we have to think about finding exoplanets in the first place. Okay, so we want to know the period. We want to know the radius of the planet itself, the size of the planet itself, the mass of the planet, and the composition. And so there's one early way to find exoplanets was the radial velocity method. And so if we look at that, we think about what's happening when a planet is actually orbiting the star. So I mentioned that planets can tug on other planets, and they'll have an effect on the orbits of the other planets. But planets also have a tug on their stars. Strictly speaking, we don't just have our sun fixed, not moving at the center of our solar system, but everything actually orbits around each other. They orbit around their center of mass, or their center of gravity. And so if we think about what's actually happening in the orbit, we'll have the planet going around, and then the star at the center has a little bit of its own wobble. And so if we imagine what that looks like, instead of looking top down, we can also look at it from the side. Be careful I'm not advancing it too fast. And so if you're looking at this system from the side, you would see something like this, where sometimes the star at the center is moving, in this case it's moving towards us, and then it's moving away from us, and then it's moving towards us, and so on and so forth. And so for the radial velocity method, the radial part comes from the back and forth motion of the star towards us or away from us, and the velocity is really just then related to that speed of that star. And the reason it's all about the star is because trying to observe the planet itself is really challenging. But stars are much brighter, and so it's easier to observe stars, to study the light of stars, and then try to figure out the presence or the effect of a planet and the signal that it has on the light from the star. And so one of the things for this method that we'll have to do is we'll have to split up the light from the star into different colors. And so this is just showing a prism. If you have white light, you can break up the light into the different colors. And so for astronomers, we will break it, instead of just saying the different colors, we'll break it up into a spectrum of light. And essentially our telescopes just use a fancy prism to do this. And so if we think about breaking up the light from a star, we'll have a different range of colors. We'll have our spectrum here, but it doesn't look exactly like this. There will be some dark lines here. This is where material in the star itself, sort of the outer parts of the gas of the star, is actually absorbing some of the light. And this depends on just some of the material that's actually in that gas in the upper parts of the star. And so, for example, maybe these lines that we're seeing are from iron. And we would know that because we can actually just take some iron, vaporize it in a lab, pass some light through it, and actually see this in a lab and measure the exact colors of light that iron would absorb. And so we could do the same for other materials. And so maybe we're seeing iron and calcium. And so the reason that this is really helpful then is because they have an exact, sort of a fingerprint, that exact color is something that we know because we can measure it here on Earth. And so when that star is moving towards us or away from us, the light from it, light as a wave, it gets shifted. And so this is something called a Doppler shift. You're probably familiar with it if you've ever heard an ambulance siren. You know, as it's moving towards you, the pitch or the frequency changes, and then when it's moving away from you. So all forms of waves will do this, and so light also being a wave will also have this shift. And so if we have a star that is moving away from us, the light will get redshifted, and so we would see those lines moving towards redder colors of light. And if the star is moving towards us, it would get blue shifted, and so we would see those lines moving towards bluer colors of light. And so now if we go back to this star that we're observing, we're just getting the light from the star. We wouldn't see the planet, but we could measure this, the spectrum of the star down in the bottom right here. We could see those lines moving, and based on how those lines are moving, we can figure out how fast the star is moving away from us. We can measure that speed, and that's telling us about the motion of that star because of the planet there. And so you want to think about planets in our own solar system. They would have a signal like this, where this would be, say there were aliens observing our solar system, maybe, PhD students somewhere out trying to do their work. They've found some planets in our solar system. This is potentially the curve that they would see from Jupiter, where the distance between the peaks there tell you the orbit period, and the height of that curve tells you the mass of the planet. And so for Jupiter, it has a signal of about 13 meters a second. For the Earth, it has a signal of about 10 centimeters a second. So in terms of the equipment that astronomers have for their telescopes, for the fancier prisms that we have available to split up the light, we're not at a point where we would actually be able to observe an Earth-mass planet orbiting a solar-mass star, basically an Earth-like planet orbiting a Sun-like star, where its orbit period is 1 year. We wouldn't be able to do that at present. We would be able to observe Jupiter. We wouldn't be able to observe our own planet. So in terms of this radial velocity method, it'll give us the orbit period, it'll give us the mass, but it won't give us these two other things. If we want to know the composition, we can kind of do that if we have both the mass and the radius, but it really just gives us two of these clues. But still, it's one of the methods. We use it because we want to find exoplanets, and so we did. So the very first planet that was found around a sun-like star was a planet called 51 Pegasi b. 51 Pegasi is the name of the star, and the B just means that it was the first planet found around that star. And so on the right here we have an artist's concept, an artist's impression of the system, where we have a Jupiter, a mass or Jupiter-sized planet orbiting a sun-like star, and on the left there, that is that radial velocity signal with the actual data points. You can see sort of how the error bars on that, for example, are fairly large. This is really why we would not be able to observe a smaller mass planet, just because it would get lost in that noise. But for a pretty high mass planet, that signal is very clear. And so there are many of these planets found using this radial velocity method before Kepler. And so from when 51 Pegasi b was found in 1995 all the way up to the end of 2008, 250 exoplanets were found using the radial velocity method. And so if we want to think about the masses of those planets in the period, it's pretty much what can be measured with this method. We can plot it on a diagram like this, and so I'll be showing a few of these plots or a few of these diagrams. So I just thought I'd talk about the axes here. So we have mass on the vertical point where I've noted a few things, where we have Mars being low with mass on the bottom. The very top of brown dwarf, that's sort of like the boundary where you have sort of like the upper limit of what you could kind of consider a planet. And then on the horizontal there, we have the orbit period. And this is not a linear scale. So for this, if we think about this, instead of having the planets of reference, we consider it just in terms of how massive the Earth is. So this is going up from something where we have something that is 1% the mass of the Earth, all the way up to something then that is 10%, something that is the same mass of the Earth, something that's 10 times the mass of 100 times, 1,000 times, and so on. And so we can put our planets in our solar system on here like this, where we have the inner terrestrial planets towards the bottom, and then the giant planets up towards the top right there. And then these are those 250 exoplanets that were found before Kepler using that radial velocity method. And so one thing to note is that they are pretty much all quite close to their star, quite short orbit periods and high mass. And so this is sort of a category up here that we call hot Jupiters. They're massive planets similar to Jupiter in mass, but they're orbiting much closer to their star. So they have to be very hot for orbiting that close. And so there were quite a few of these found, and also a lot of these cold Jupiters as well. So there's a question, are these common types of planets? And it really just is because the radial velocity method is better suited towards picking up these high mass planets. And so it's not that, if we're using this method, it's not telling us really anything about how common the planets in our solar system are. It's really just telling us something about how good this radial velocity method is at finding those types of planets with those blue markers there. And also 250, although it sounds like a lot, really isn't enough to figure out much about how common the solar system is. And it's really, the number is sort of smaller because in order to get that spectrum, astronomers have to dedicate a lot of time to observing these individual stars. Have to use a lot of hours with the telescope. It is quite a lot of time, very time-consuming process. And so in order to really figure out how common our solar system is, astronomers had to use a different method to find planets that was better suited to doing really large surveys. And so we're going to talk about the transit method next, and this is what Kepler used. And so thinking about the transit of a planet is potentially something that is somewhat familiar because we have transits of planets in our own solar system. So this is showing actually a transit of Venus from 2012, passing in front of our star, our sun here. And so a transit really is just when a planet in its orbit is moving in front of the star, and it blocks a little bit of that star's light because the planet is literally just in front of it, blocking some of the light. So the star will dim. It's not really something that would be noticeable by eye. You wouldn't notice the sun dimming. You shouldn't look at the sun with your bare eyes. You wouldn't notice the sun dimming when Venus is transiting it or Mercury is transiting it. But we can have detectors that can notice it. But one thing to notice, when we look at stars, for our sun, we can get really great high-resolution photographs of it because our sun is close to us. But for other stars, we're really just seeing effectively a point of light. We're not going to be able to actually resolve or to see that planet itself, to see that disk of the star with this, the planet passing in front of it. We're not going to be able to see that. We're really just going to get the light of the star pretty much as a point when we get it in our cameras. But we can think about then what happens when this light from a star is on our detectors. And so for telescopes, we typically use a CCD with 100 pixels. This is similar to the camera that's going to be in your cell phone or a DSLR, where it just has a detector with a grid or an array of smaller detectors that can pick up light and just measure how bright the light is that it's receiving. And so for stars, it might get spread out over a few different pixels, a few different cells. But then you can see that as the planet is passing in front of it, you might be able to see it dimming. And I don't know if this has started. This is a video. It's just that you probably won't be able to see it by eye. And so I have a version where I enhanced the contrast, but we'll see if my clicker is working. Maybe I have to do it one more. Do you see the flicker? It might be a little hard. I might dim it temporarily. You see the flicker?
Yeah.
And so this is pretty much, I mean, what the camera is seeing. However, it would take a very long time and a lot of PhD students to just stare at images like this. It wouldn't be very effective. And so what you can actually do is use the information that's actually going onto the detectors effectively just to combine what's being smeared out, combine it into one number to say how bright the star is. And then if we imagine what is actually happening when we measure the brightness, when the planet passes in front, you get a dip in the brightness, and then when the planet then moves away from the star, the brightness will go back up. And then based on how deep that dip in brightness is, that'll tell you how big the planet is, the size of the planet compared to the size of the star. And then based on how frequently you get that dip, that'll tell you the orbit period of the planet. So for this transit method, it'll give you the orbit period, it'll give you the size or the radius of a planet, but it will not give you the mass and it won't give you the composition. But it'll still, these two pieces of information will still be able to tell us a lot. Okay, so now we're ready to go into Kepler, the big thing that tonight's talk is all about. And so this is an artist's rendering of the Kepler Telescope, and okay, so the Kepler Telescope is in space. It's currently in space. It's been retired, but the telescope itself, in terms of the mirror of the telescope, this is showing the size of the mirror on the telescope. It's smaller than Hubble, but as a space telescope, it's a little less than 1 meter in size. It's pretty impressive, for a space telescope. That'll still give you a lot. And if we think about, many of you have probably seen these gorgeous images from the Hubble Space Telescope. So some of that is because it has this large mirror. Some of that is also because it's in space. It doesn't have the Earth's atmosphere to distort the light, and so it can get really nice, crisp, high-resolution photographs of different things in space. And so some of that really is just from the size of it. But you can get similar kinds of images with the Kepler telescope. But whenever you have a telescope, you can sort of have a trade-off between how nice the resolution is, how sort of fine in detail you can see in a photograph, and how big of a patch of the sky you want to stare at. So the finer detail you want to get in an image, you would be staring at a smaller patch of sky. And if you want to sacrifice the detail, you can put a larger patch of sky with the same telescope. And so for Kepler, really just wanted to measure the brightness of stars. And you're never going to be able to see stars in nice, fine structure, no matter how big your telescope is. That's just pretty much never going to happen. So for Kepler, it didn't use this to have nice high-resolution images. Instead, it used this mirror, the size of this mirror, to look at a large patch of the sky. And so I did it. This has its camera. It has sort of this grid here with a whole bunch of different detectors. It's a really nice camera, but I won't go into too much of the technical details. But I just want to show the patch size. It has the corners don't have anything there, because you'll see that shape here when we're seeing the field of view, as we call it, on the sky. And so this is a patch of sky that the Kepler telescope looked at. And it looked at it, we can say it looked at it unblinkingly. It monitored this patch of the sky for a few years, just staring at the light of the stars, collecting the light of the stars to measure the brightness and see how that brightness changed. And in terms of where that field of view is in the sky, it's actually near the summer triangle. I kind of drew it on here last minute, so I don't think that's actually, I think I messed it up. The stars to the right of that telescope, where you have Altair for the other star in the summer triangle. But in the spring and summertime, if you ever identify the summer triangle, you pretty much are then looking at the Kepler field of view in the sky, which means even though your eyes can't see them, you are staring at basically more than half of the planets we know about in our galaxy, which I think is pretty rad. Oh. So Kepler is orbiting the sun, and so it's in a very similar orbit to the Earth, but not quite the exact same. So it trailed behind a little bit. But in order to look at that patch in the sky, one of the things you'll notice with these images as it's going around is that the telescope has to rotate and move around to make sure that it's always pointed at that one patch in the sky, to make sure that it's not getting light from the sun coming into the telescope, because that would mess up how you can monitor the light from all those other stars. And so being able to point and rotate and turn around to look at that patch of sky is really important for Kepler. So it had these reactor wheels to do it, and it was working really great for a little while, but we'll get back to that later. And so to have a space telescope, it has to launch. So I don't know if like anytime you're stressed, I had a supervisor for a project I did after undergrad. So whenever she was stressed out, you know, it was like late at night and she just needed to do something to unwind, she'd go on YouTube and watch videos of rocket launches. And they're really fun to watch. I don't know if you've ever watched any of them live, but this is the video of Kepler launching. It was on a Delta 5 rocket. Beautiful launch. It's wonderful. I highly recommend watching them. I always figure out, I watched, there was a space station for the Dragon crew, and I got up at 2 in the morning to watch it. It was great. It was wonderful. Okay, so the Kepler was launched, and so this was actually pretty much a decade ago. On March 6, 2009, Kepler was launched and worked really well. We had to do a few things just to make sure that it was working fine. So the first few months were dedicated just to make sure that all the equipment was working. But within about 6 months or so, they were ready to actually start taking observations. So now we have the big question: what did the Kepler telescope find? And so this is an orrery. And so what we're seeing here is we have our solar system at the center. And the scales here aren't exactly right. But pretty much every single other one of these moving systems is a system where you have a star and at least one planet orbiting around it. The size of the circle tells you something about the size of the planet. And the color tells you something about the color, the surface temperature of that, where anything that's dark purple is going to be something that is similar in temperature to the Earth. Anything that is bluer, greener, or yellow is just ridiculously hot. So there's a lot of yellow because most of these planets are just ridiculously hot. And then this is actually just showing the space in our solar neighborhood around us in our galaxy. And so while it's wonderful to look at that video, it's very pretty and mesmerizing to watch. It's a little bit more informative, again, to go back to one of these plots like this, where we can look at the orbit period and the radius or the size of that planet itself. And so we can compare that to the Earth, where again we can start where we have something that's half or 50%, 60%, 70, 80, 90, and then 1, and then we go 2, 3, 4, 5, and so on with this scaling here. There we go. So all of those blue dots are planets that were found in the first part of Kepler, the sort of the first phase of Kepler, and those pink ones are the planets in our solar system. And so again, we have some of those planets that are found were hot Jupiters, but compared to those radial velocity planets, there were a ton more planets in smaller size that Kepler found. And so you'll notice that a lot of these, they're smaller than the giant planets. They're bigger than the Earth, though, and so you can call these super Earths, but there's a huge number of planets in here. And one of the things with the transit method is that, if you have a larger planet, if you have something that's 10, 20 times the size of the Earth, that's going to block more starlight, and so it's easier to see that signal. And so if those planets existed around the stars that Kepler was looking at, Kepler would have seen them. And so the fact that there are so few planets above where these super Earths are tells us something, that these hot Jupiters actually really aren't common. It was just that the earlier observations with those radial velocity method were really just sort of biased towards finding those. Whereas Kepler was still biased towards finding them, but was able to monitor more stars, able to see that they really weren't common. But these super Earths are incredibly common. So they're larger than the Earth. And so maybe they look something like this, where we have, larger than the Earth, but still rocky planets, where we can imagine these artist concepts of these other strange worlds, except these actually aren't artist concepts of planets. I hope I tricked you. These are actually frying pans. They look like planets. Another thing that these could be are mini Neptunes. And again, again, this is because they're smaller than Neptune, smaller than Uranus in size. But the difference there, if we think about a super-Earth versus a mini-Neptune, is really just, for a super-Earth, it's basically a scaled-up Earth, where it's really rocky, because it still have a fairly small fraction of its mass or fraction of its weight being an atmosphere, a gas atmosphere, whereas a mini-Neptune would be a scaled-down version of Neptune, where it has a pretty thick, extended atmosphere. And this is something we can't figure out just by having this radius or the size of the planet. We could perhaps have some worlds that look like this, where they they have a really, pretty substantial part of their size or their mass in a gas atmosphere. Let's think about some of the actual worlds. Just a few highlights of things that Kepler found as well. So the very first rocky planet that Kepler found was a planet called Kepler 10b. And so this is a super-Earth. In terms of the size, it's a little bit smaller than twice the size of the Earth. And if you look at its orbit period, it's orbiting 1 day around its star. It's incredibly close to its star. And so this is a lava world. It is so hot, the entire surface would be molten rock. And so we can imagine, this is our concept, this would be, the sunrise on Kepler 10b. The floor is literally lava. This is definitely not a planet with people on it, but it's pretty incredible that the very first rocky planet that Kepler found was something so bizarre, something so incredibly different from our own solar system. Another interesting planet that Kepler discovered was a planet called Kepler 16b. So again, the Kepler 16 part, the Kepler 16, that's the name of the star, and the B just tells you that that was the first planet discovered around it. And so for Kepler 16b, this artist concept we're seeing here, we have a planet. If I go back, you can see it's a Jupiter-sized planet up there, with an orbit period of around 1 year. And so the planet here is that smaller dark spot though. The big yellow thing you're thinking is a star. The red one is also a star, because this is a circumbinary planet. It is orbiting a binary star system, where there are two stars orbiting each other, and then their planet is orbiting around both of those stars. And so this is pretty much Tatooine. But it's actually kind of incredible to think that, Star Wars came out 1970 something, over the year. But that, sometimes sci-fi really does predict these bizarre things that end up becoming true. And it's super weird and wonderful, and it's one of my favorite things about sci-fi. There actually is really awesome travel posters. I don't know if any of you have ever seen these from NASA. They have these really cool posters. It's for our solar system as well. For Kepler 16b, your shadow always has company. So thinking about planets with life, Kepler 16b is a giant planet. It's not going to be like Tatooine. Tatooine had a solid surface for Luke Skywalker to walk around and on the sand. But if you want to think about planets thinking about life, we generally, the best thing we can do at present is just to think about the surface temperature of a planet. And so if planets are far, depending on the size or the period, we could just make some assumptions about their atmosphere. It's the best we can do for now. So if they're orbiting too close, their temperatures are going to be high, they're going to be far too hot. If they're orbiting farther away, they have longer periods, they're going to be too cold. But if they're in this range, where we have sort of somewhere between 0 and 100 degrees Celsius, it's just right. And the reason we say it's just right is that it can have liquid water. So this is what we call the habitable zone. I personally don't really like this term because it suggests that we know that this is a planet that is habitable, but we don't actually know that. Another word we could use for this is the temperate zone. It doesn't sound as cool, but it's a better description of what we actually know about that planet. But if you want to think about some of the planets in terms of the temperatures that Kepler found, there's one in particular that I'll highlight. Oh dear, I lost. Okay, so Earth is, Gary knows, a sanity check. Earth is in the temperate or habitable zone. That's good. Earth is habitable. We do know that for sure. But there were a few of these, but what I'll highlight is, Kepler 186, clicking too fast. So it's just a little bit larger in size than Earth. It's pretty similar in temperature. It's a little bit cooler on the surface. And so if we imagine what this looks like we have this Mars rendition here, where it's orbiting its star, lovely, rocky Earth-like planet. But the star is actually smaller than this. So it actually has very red surface in terms of its planet life, perhaps. Again, with these travel posters, they're gorgeous. I recommend looking them up. Google NASA travel posters. They're phenomenal. So I could spend pretty much the rest of the talk just like picking out little, individual Kepler systems, Kepler planets. But I do want to move on from individual planets and thinking about systems of planets now. And so the ones I've highlighted here are part of a system. They're orbiting a star called Kepler 11. And there are 6 planets that we know about in this system. They all have really, fairly short orbit periods. They're all fairly large in size. And so this is what we call a compact system. The planets orbit very close to their stars and very close to each other. And so, again, the stars, Kepler 11, if we imagine placing this system, sort of on top, comparing it in size to our solar system, 5 of these planets would fit within Mercury's orbit, and then the 6th one would fit within Venus's orbit. It's incredibly compact. So we know about more than just Kepler 11 for these compact planetary systems. And these are the ones that I study, so I obviously have to talk about this for a little while. So this is pretty much how I view the solar system on a regular basis. So we can think about the size of the orbit relative to Earth, where we have Earth being the 3rd planet. Its orbit size we can describe as 1. And then we can compare the other sizes of the orbits for our planets to that. And again, with this scale, so we're starting at something that's 1% the size, 2%, 3%, so on up to 10%. Then we have 10%, 20, 30, 40, up to 1. And then we have twice as large, 3 times as large, and so on and so forth. And so we can put up a whole bunch of these other compact systems in comparison. And so there are a whole bunch of these that have at least 5 planets orbiting their star. For the most part, they're all super Earth in size. Some are a bit larger, where they have ones that are more sort of like Neptune or Uranus in size. And then they have giant planets that are quite close to their stars here. But one of the things we can also do is to switch back to what Kepler actually would have observed, which is the orbit period here. And again, noting that, for the most part, all of these are orbiting within the orbit period of Mercury, their own solar system. They're very, very different from the solar system, where pretty much all of the planets are orbiting ridiculously close to their stars. One of the things, I'll go back to this idea we've talked about a few times, which is that for orbits, it's not just a planet orbiting the star because of the star's mass or the star's gravity. But the planets also have gravitational tugs on each other, and that can affect and change their orbits. And so they're pretty small tugs, but they can build up over long enough periods of time. So if we think about the lifetime or the age of these systems, we can do it in comparison to the orbit period of the closest planet to it. So for our solar system, that's Mercury, and so for the age of the solar system, it's about 4.5 billion years old. Mercury has had 20 billion orbits. For these other systems, they have had a lot more. They've had hundreds of billions, even to trillions of orbits around their stars. So they're pretty similar in absolute age to the solar system, but just because our planets are so much closer, they've had so many more orbits. And that's just a whole bunch of extra time for these little tugs that the planets have on each other to build up, change the orbits, and it could lead to catastrophic things. As the orbits get tugged and pulled, the orbits can get stretched out until planets are actually able to crash into each other. They could get kicked into their stars. And so this is like literally what keeps me up at night. I really want to understand why these systems have survived. Why are these the ones we're seeing? What has happened over their really long histories? And what has potentially then happened to systems that were maybe more compact, even more compact than this? When they've had their catastrophic ends, is it possible that we could have some signature of that from what's left behind? But I can't talk about that forever as much as I would like to. Feel free to just ask me about that afterwards. I have to carry on. And again, I can just keep talking about the different observations from Kepler, but I should sort of reel it in, bring it in, and think back to comparing the planets in our solar system, asking how common is our solar system. And one of the things, again, highlighting our planets here is that we think about the sizes of the planets that Kepler found, but also the orbit periods, there's pretty much just nothing where the planets in our solar system are. And one of the big reasons for this is just this right-hand side of this plot, that Kepler did not find a lot of planets with long orbit periods. And I mentioned, Kepler launched a decade ago. Why hasn't it found planets with several year orbit periods? And this is because in 2013, 2014, tragedy strikes. And it's a little bit of a hyperbole, but I was talking about, in order to look at that patch of sky, that the telescope needed to be able to turn itself to always point and stare at that patch of sky that it had for its field of view. And it needed to have those reaction wheels to turn it. If you want to turn yourself in 3 dimensions, you have to have at least 3 angles to turn yourself. And so the telescope had 4 of these wheels, just in case one of them broke. And then one of them broke. That's fine, it still had 3 wheels. Then the second one broke, and it could only turn itself in 2 directions. And this meant that the telescope was no longer able to keep itself pointed at that patch of sky. And so this brought an end to the first phase of the telescope's mission. And people were thinking, okay, we have this telescope in space. It would be a shame if we just couldn't use it anymore. And so I'm absolutely amazed at what people did to figure out how they could still use Kepler. And so this started the second phase of Kepler's mission that we call K2. And so what astronomers decided to do was, with the 2 wheels that it still had, that it could still turn itself around, it would orient itself and then also use what we call radiation pressure from the sun. Essentially the light, sort of like a solar wind, the light actually pushes on the telescope, and it can actually have a bit of a pressure on the telescope to keep it balanced. And so it isn't able to stare at that same patch of sky, but it was then able to stare at a patch of the sky for a little bit over 2 months at a time, by using the light from the sun and the 2 wheels that it still had working to keep itself balanced for a little bit over 2 months at a time, looking at different patches of the sky to keep looking for planets around our solar system. And what's incredible is that you're seeing here is that this is a different view of the spacecraft. Is that, and the yellow here is showing light from the sun, the solar wind, but that it's an incredibly delicate position to have it actually be stable. It blows my mind. Like, I do theory. I sit at my desk and do equations, calculations if I can, do things on my computer. It's pretty straightforward as far as I'm concerned. Like, this just blows my mind that people were like, okay, we've got a spacecraft we can't travel to. We have to figure out how we can turn it to get it be perfectly balanced. We can only send commands to it and hope that it works, and it did. But also that people were like clever enough to come up with this, I think is really wonderful. Okay, and so showing it then as it orbits the sun, that for that period of time of 83 days, it would have just a particular patch of the sky that it could look at for that time period, and it would move along its orbit and have a different patch of the sky that it would look at for another 83 days, and so on. And so these patches of the sky were different. This curve here is just based on the orbit. It's called the ecliptic plane. And it's pretty much just based on the orbit of Kepler around our sun, essentially being the same orbit as the Earth. And so these are just the different patches of the sky that it's stared at. And so we can really summarize all the planets that the telescope found here, where the blue ones, again, are the ones found in the first phase of the mission. These pink ones are the ones that were found in the second phase. And you can really see, again, that 83-day window that it had to look at a patch of the sky. That none of the pink points are orbit periods longer than that time period. But it still found, again, so many more of these super-Earth or mini-Neptune planets, which is incredible. And so in 2018, the telescope was retired, it just ran out of fuel. So one of the things, in order to keep it pointed and moving, to orient it in different patches, it did have to use fuel. And so anything that has a limited supply, it's going to run out. And so pretty much all of 2018 were like these notices. I'd see something posted on Twitter or Facebook, because scientists pretty much also just have their social media groups where they spread rumors and gossip, being like, oh no, Kepler has gone down, there's a service alert, something's gone bad with it. Or would have these safety shutdowns, be like, oh, is it gonna turn back on? Okay, is it gonna download the data? Is it gonna be able to go on to the next cycle? And eventually, it had its last cycle in the end of 2018. But this here is showing, again, so these blue, the blue points here in each individual year, just the total number of exoplanets that were found with all different telescopes that people were using to find planets. And the orange is a contribution from the Kepler Telescope through both phases of the mission, with the first phase, we just called Kepler, and then that K2 phase as well. And you can see in a couple of years, in 2014 and 2016, there's just a stupidly high number of planets that it found. So in the early years with Kepler, people were really looking at the data, for the most part by eye, to try and find those dips in brightness. And then once people started to understand what these curves looked like, what the data looked like, they were able to then have programs, write algorithms, use code to pick up the signals from the planets. And so in 2014 and 2016, they just had automated processes to pick up a whole bunch of, and confirm a whole bunch of planets from that data. There are over 2,600 planets found, which is over half of all planets that we know about. And so what are some of the things that we were able to learn from the Kepler mission? And so I think one of the coolest things that has come out of the Kepler mission is that we know that planets outnumber stars in our Milky Way galaxy. That on average, there is at least one planet per star in our galaxy. There are, approximately 200 billion stars in the Milky Way galaxy. That means there are at least 200 billion planets in our galaxy. It really says a lot just about the survey, the mission of Kepler to look at 200 billion stars, but based on the patch of sky, the different patches it was staring at, that we're actually able to make that statement pretty confidently that just with the numbers we have, that planets really do outnumber stars. And it's not that each one really has one. There are a lot of stars that have no planets orbiting around them. But one of the other things is that 30% of sun-like stars have Kepler systems where they have multiple planets orbiting around them. And again, pretty much most of these planets are super-Earths around them. This was entirely unexpected. We don't have a super-Earth in our solar system. We just have Earth and then Neptune. We have no idea what this gap in between is like. And it's still one of the big mysteries. And so for smaller stars, really they tend to have, even cooler than our sun. Pretty much it's typical for them to have 2 or 3 small rocky planets around them. Which I think is pretty incredible that these multi-planet systems are actually, all things considered, quite common. And so, despite all of these wonderful things, our solar system is not common. We talk about these compact systems. Kepler found a lot of incredibly hot worlds. They're just very different from our solar system. And so, this still brings up a lot of questions. If we're not common, does it say something about our habitability? You can think about that. But again, these are just really big questions. As much as I would like to talk about them forever, I think really the big thing that we can say quite confidently from the Kepler mission is that our solar system is not at all common. So very quickly, I'm going to talk about a couple of missions that are happening right now or upcoming. One of them is called TESS. It's the Transiting Exoplanet Survey Satellite. And so this is looking at, it's not looking at a fixed patch in the sky for several years. Instead, it's just looking at some of the brightest stars in the sky. And what's great about this is looking for transits, but because the stars are bright, they're really good for also doing radial velocity searches. And so one of the things with TESS is that we'll be able to get both the size, the radius of the planet, and the mass, which means we can learn a lot about the compositions of these planets, in particular of these super-Earths that we don't know, or these mini-Neptunes. For a lot of the planets that TESS finds, we'll be able to figure out, are they more rocky, or are they more gas? Are they sort of miniature versions of Neptune, or are they scaled-up versions of Earth? There's another telescope called LUVOIR. That stands for the Large UV Optical Infrared Surveyor. If there's one thing to learn about astronomers, is that we love acronyms. And so this one has a huge, this is a planned one, so this is an artist concept of it. TESS has launched, it's already found planets, it's wonderful. This one, still many years away. The big square on the bottom is a sun shield to block out the sun. And then it has an absolutely huge mirror. This will be a huge technical challenge. But this will be really great because it's going to, the plan is to be able to look at the atmospheres of planets like super-Earth, even if they have thin atmospheres, because this will be able to tell us a lot about their surface temperatures. Again, thinking back to Mercury versus Venus in our own solar system, the temperature of these planets, whether they could have liquid water on their surfaces, whether they have water in their atmospheres, really depends on being able to get really good observations of their atmospheres, which isn't something that our current telescopes are able to do. And so it's still unknown, even with all of this. I think one of the big unknowns for planets is really just thinking about sort of the bigger picture with planet formation, their long-term changes. And so this is something that astronomers are still piecing together. We have some of the bigger picture still figured out, but there are still a lot of clues about how we actually are able to build and assemble these systems, in particular these compact systems, but even our own solar system. There are still a lot of puzzles. We know that they have to form, we know that they're common, it has to be a fast, efficient process, but we still have no idea. We can't run a simulation on our computer from start to finish and have it work out perfectly. There's still a lot to be figured out with exoplanets and planetary astronomy. And with that, I'll leave things there and thank you and take a few questions. For questions, but just for the sake of everyone moving forward. So there's a woman over here, yeah.
Is there any kind of correlation between the stars that do have compact kind of planetary systems, and do you just think that our solar system seems weak because the key planets that have a long period, we just never see them transit in kind of
Yeah, that's a good question. So the question is, with these compact systems, it's really hard to go back to my slides, but with these compact systems, is it possible that they have longer period planets that we just weren't able to observe? And within a few years ago, I would say we're not sure. More recently, it seems like they probably do have giant planets. There's another graduate student here, she had a paper that came out a couple months ago saying that it's really probably common for these compact systems. Or should I say the other way around? If there's we call it a cold Jupiter, something that's the size of Jupiter, one of these giant planets, that's on a few-year orbit period, that is quite common to have that with one of these inner compact systems that have these smaller rocky planets. It's just that they're harder to see transit. So with Kepler, we didn't see a lot of those, but it's just, they probably exist. And that's something that really, I'm sort of diving down that avenue.
the question about the compact. I meant, is there a correlation between the stars? Like, are they brown dwarfs or something like that?
Oh,
and
so
then that other thing was another.
Okay, so in terms of the stars, for the most part, the ones that Kepler was observing are just sunlight stars in terms of their temperature, so sort of how bright the stars are. So there's sort of a correlation in that sense, but that's mostly just because of what Kepler was designed to look at. But we do see them around a huge range of stars. So there's a question up there. Yeah.
Yeah, thank you for your talk. It was very interesting. I have a question about the graph that you showed that you compared different solar systems based on the orbit time on the horizontal axis. I was wondering why we can compare them based on the orbit time. Isn't it like a mass of their own stars also part of this, shouldn't be part of this graph?
I'm just bringing this up.
Yeah, this one.
Yeah. So in order to get the orbit size, so Kepler did measure the orbit period. Oh, that's too far. Kepler did measure the orbit period, and then exactly you're right. So in order to actually go from the orbit period to the orbit size, you do need to know the mass of the star. But for most of Kepler's stars, we do know that, and so these orbit sizes, you can just do that calculation once you know how heavy or how massive the star is. Yeah, so in the interest of time, we're going to move on, but I will be